Welcome back. It's time for video 4 as we continue our work in Unit 2 for our studies of Math 109. So with no further ado, let's go ahead and share a PowerPoint here. All right, from the current slide. All right, this slide makes reference to a phrase that you heard on the last video. The cardinal number, or the cardinality of a set, simply describes how many elements are in this set. And you see the notation out there in red. It's a lowercase n, and then the set that's being discussed is inside parentheses. In this case, it's set A. So I thought, well, you know what, let's throw an example out there. So there, if you say, well, dang, Dell, there aren't many members of set A, I would agree with you. Looks like there might only be 3. So we would say that the cardinality of that set is 3, or the cardinal number of that set is 3, and we would write it that way. This one makes my head hurt because as a Packer fan, I break out in hives when I see Eagles players. But again, there aren't many members of that set, and it looks like there are only 2. So the correct notation says the cardinality of set B is 2. There are 2 members in set. All right, I should point out that it's possible for a set to have no members, all right, in which case we have symbols that have those braces with nothing inside, or a symbol that some of you remember from before, that the null set symbol, the 0 with a slash. Be careful though, don't do that set of brackets with the empty set symbol inside. That set's not empty. That set has a symbol, that set has a member. It has as a member the symbol for null set. So don't do that. Either of the other 2 is fair. I like the little circle with a slash. I'll probably use that more often than not. So those are sets that have nothing in them, and they would have a cardinality or a cardinal number of 0. Finites and infinites. So a set can be one or the other. You can either count all the members and eventually be finished, or you can't count all of the members. The real numbers are infinite. They go on and on and on. So we could represent them with the use of the ... business. The integers are infinite. Same kind of an idea. The ... dots would be helpful. The number of people in this room, provided we were all in a room, would be finite. We could count them. We could actually say this is the last person in the room, and we would not have any other people. So finite says you can count them all. So the cardinal number is either 0 or 1 or 2 or 3 or some natural number. Okay, so if you can count them and eventually be finished, the set's finite. If you can't count them, the set's infinite. I like Venn diagrams. Might be a new player for you. Generally, when you use Venns, it references a set that we call the universal set, everything that's possible in this discussion or in this set of relationships. Usually that's represented with the letter U. Okay, and then the complement of a set is defined to be all of the members of the universal set that aren't members of the set that we're discussing. We'll check out some examples here to make sure this makes better sense. I should point out that different books use different notations for complement. Your author has a horizontal bar across the set name to represent complement. I have seen some books with a little superscript C next to the set name for complement. I've seen some books use like a little prime, like you've seen maybe for the use of derivatives for complements. But we'll stick with what your author stays with, and that should be fine. All right. Set builder notation says if you're talking about the complement of set A, again, that's got that horizontal bar across A. It's consisting of all the members X such that X is in the universal set and X is not in A. So the complement is everything that's contained in universal, but not contained in set A. So here's some examples for us. So our universal set has only certain things. It's got 2, 4, 6, 8, and 10. Set B's got a 6 and a 10. Set A has a 2 and an 8 and a 10. So if somebody says, well, what's not in B? What's in the complement of B? Well, there are a lot of things that aren't in B. Pepperoni pizza's not in B. Ice cream's not in B. But when we answer things relative to the complement of B, we are restricted to the members of the universal set. So if we look at that universal set and say, who's there who's not in B? Well, 2's not, 4's not, 8's not. So the complement of B would be the set that consists of 2, 4, and 8. The members that are in the universal set, not found in B. Kind of the same game for the complement of A. A's got a 2 and an 8 and a 10. So we're looking for everything that's in the universal who is not 2 or 8 or a 10. Looks like that might be just B4 and 6. The last one here is a little sneakier. The complement of the empty set. Now, the empty set's got nothing. So everything that's in U that's not in the set that has nothing in it would basically return all of set U. So it would be 2, 4, 6, 8, and 10. Everything that's in U that wasn't in a set that had nothing. All right, so 2, 4, 6, 8, and 10. All right, so we got U is defined as the set of all X's such that X is a professor at Immaculata University. And set B says, let's talk about X such that X teaches math 109 this semester. Hey, guess what? There aren't many people teaching math 109 this semester. It's me. So if somebody says, describe what's in the complement of B. Well, dude, the only thing that's in B is Del Furster. That's it. So if you're going to describe the complement of B, you would list any professor at Immaculata, because remember, you're bound by the universal set, but you would not list Del Furster because he is, in fact, the cat who is in set B. Subsets, little symbol out there. Honestly, I get myself twisted. You're going to see another symbol coming up, and every year I teach this course, I have to remind myself which is which. All right, so for two sets, A and B, B is defined to be a subset of A if everything that's in B is also found in A. Every element of B of set B can also be found in set A. Some things you should note, all right, in red. Every set is declared to be a subset of itself, and the empty set is also declared to be a subset of every set. So those two caveats are there just to keep us straight. Okay. Here's another notation. This is proper subset. You'll notice it doesn't have that little horizontal bar underneath. All right, so it's a proper subset. First of all, if it's a subset, and if the two sets are not the same. So in effect, for it to be a proper subset, there has to be at least one element of set A that's not found in set B. They can't be identical. Here's the picture for you. All right, set B is a proper subset of set A. There is something in A that is not in B. All right, so in this case, we would say that B is a proper subset of A. It's also correct to say that B is a subset of A, but proper subset's a little more stringent. There's at least something in A that did not get included in B. B is a proper subset of A. All right, so if somebody says, tell me how many subsets a set has, you basically say, well, it's either going to be in or not in when I list the subset, and that's where the 2 comes from. It's either in or not in. There are 2 options, and if there are n elements in the set, you're going to make that decision for each of the n elements. So if you want to say how many subsets are there, it's 2 to the power n, where n details how many elements are in the given set. So if by chance the set had 3 elements, there would then be 2 to the third or 6 subsets for that particular set. If you want to show off, we call that set of subsets the power set. So if someone says, list all of the subsets for this set, they're asking you to list the power set. All right, we're going to do this one. I figured once upon a time kids would know who John, Paul, George, and Ringo were. So you'll notice there are 4 elements of this set. So according to that last slide, there should be 2 to the 4th or 16 subsets. Here we go. Ready? Let's list them. These first 4 contain only one element of that group. There's a set that's just John, a set that's just Paul, a set that's just George, and a set that's just Ringo. Now we'll turn our attention to trying to list sets that have 2 of them. All right, so here we go. We can do John and Paul. We can do John and George. We can do John and Ringo. That's it with John. We can do Paul with George, Paul with Ringo. Remember, when you're listing sets, order doesn't matter. So the fact that you looked at John with Paul, don't get cute and say, well, I got Paul and John. It's not a different set. All right, Paul with Ringo, and lastly, George with Ringo. So we had 6 sets that had 2 of the elements. We could look at sets that might have 3. We could have John and Paul and George. We could have John and Paul and Ringo. We could have Paul and George and Ringo. We could have George and John and Ringo, and I think that's it for sets of 3. The last 2 are sneaky. You can, in fact, have all 4. Remember, every set is a subset of itself. Well, that's pretty spiffy. And the last of our 16 subsets is the empty set. So those last 2 I saved until the end because they're the ones that are going to cause more stress. And one more spinny for the empty set. So yeah, 4 elements in the set. If you count them all, that was 16 subsets. We did great. All right, that takes us to assignment 2B. Problems from your textbook, pages 62 to 64. Grab your loose leaf, grab your online, whatever. It's quite a few here. Some information with sets, get some practice, and send me the solutions at the Dropbox for assignment 2B. That, my friends, wraps video 4. One more to go on video sets for unit 2. We'll be back shortly. See you then.